So the question is, the sliders A and B are connected by a light rigid bar and move with negligible friction within the slots, both of which lie in the horizontal plane. For the position shown, the hydraulic cylinder imparts a velocity and acceleration to slider A of 0.4 meters per second and 2 meters per second squared respectively, and both to the right. So determine the acceleration of slider B and the force in the bar at this instant. So this question is going to be relatively long. The first step that I'm going to take is to draw free body diagrams of the two different blocks and sum the forces on both of them. The third step I'm going to have to take is looking at the geometry of our situation and working out a relationship between them, where if we take the derivative then twice of that equation, we end up with a third simultaneous equation to be able to solve. So the first step, as I said, is going to be free body diagrams. So let's start with the free body diagram of block B here. Sorry, A. So the forces that are going to be acting on this block, one of them is going to come from this cylinder. So we're told that it's going to pull the whole thing to the right. So that means the cylinder is going to have to impart a force, which we're going to call F cylinder, also to the right. We're also going to have a force due to the bar that's attached. It's going to act up this way. I'm going to call it T for the tension in the bar. And the last force that we're going to have is the normal force, N. And that force is going to be keeping it within the slot, and it's applied vertically because it's perpendicular to this horizontal surface here. So I guess it's probably good to note that the reason I'm not putting gravity in here is because we're told that this lies in the horizontal plane. So that means that the gravity vector essentially is through the page. It's not in the 2D picture that we're drawing. So the only other thing I'm going to add to this diagram is just the angle, and we're told at our instant it's 30 degrees here. So I'm going to use a normal X and Y coordinate system to sum the forces on this block. And we're going to look at the forces acting in the X direction because that's the direction this thing is going to be able to move. So this is our equation. Now in the X direction, we're going to have the force of the cylinder minus T cos 30 from the bar. The N is in completely the Y direction, so it doesn't make its way into this one. And on the other side, we have the mass of the block, which is MA, multiplied by its acceleration, which is AA, or I'm going to call it AA. And we know that this block is only able to move back and forth in the X direction, so this is its overall magnitude as well. So at this stage, we have too many unknowns to solve directly. We don't know what the force in the cylinder is, and we don't know what the tension in the bar is. However, we do know the mass and the acceleration, but I'm just going to leave it at that for now. So I'll scroll back up, and this time we're going to follow the same procedure, just with block B. So again, drawing it. So forces that are going to be acting this time, again we're going to have the tension force due to the bar, and we're going to have a normal force acting perpendicular to this surface to keep it inside the slot. So that's going to be here. Alright, now from the geometry we can work out that the angle in here is going to be 30 degrees from the Z rule. And because this is 60 degrees here, you can work out that the normal force is going to be 30 degrees because it has to be a right angle between, the block and this N force. So this time I'm going to define my coordinate system slightly differently. I'm going to have the Y in line with the slot, and the x direction is 90 degrees to that. Alright, and that just makes it easier because now if we sum our forces in the y direction, it means that the acceleration is going to be completely within that y direction. So let's do that. So both of these are going to have, sorry, this one only is going to have a y component. This n vector is completely in x. So the y part is going to be negative t, and it's going to be the sine component. And it's going to be sine of 60. I'm going to add the 30 and the 30 together. It's equal to the mass of the block, which is mb, multiplied by the acceleration of the block, which is ab. So again, we know what the acceleration, we know what the mass actually is, but we don't know the acceleration and we don't know the tension. Okay, so between these two equations, we have three unknowns, but only two equations, so we're not going to be able to solve it directly. So this is where the third equation comes in, which is probably the hardest one to get, definitely the hardest one to get, and it's going to be from looking at the geometry of this shape. So let's redraw the triangle that we've got, and what we're going to do is call this side length here xb, and this side length here xa, and we know this length here of the bar is always going to be 0.5. So I'm just going to scroll down. So this is what that triangle looks like. Actually, I'll just leave this off. So we've got XA, XB, and L. Now, we knew this angle in here was 60 degrees, alright, and it's going to be a constant angle, alright, same with this one in here. The reason is the slot means that this vector, this XA, always has to be lying on that line. XA is always going to be horizontal. All that changes is kind of the angle in here and the angle in here and the lengths of these two lines. Alright, so that's going to be important when we're going to write out our equations. So we're going to have a different color. So this is constant at all times. Alright. XA and XB, they're going to be functions of time. Alright, same with the angle here and the angle here. They're going to change depending on what, XA and XB lengths are. And that 120 degrees is going to be constant at all times too. Alright, so this is going to tie into when we take the derivatives in a second. So in order to get a relationship between XA and XB from this triangle, we have a choice of using the sine rule or the cos rule. Now, what I'm going to recommend is using the cos rule, simply because the cos rule only takes one angle, and we can use this constant one. Alright, if we use one of these other angles that's changing with time, when we take the derivatives, it's going to be much harder. Alright, probably even, very, very, very difficult. So we're going to use the cos rule, and we're going to use this angle inside it. So it's a squared equals b squared plus c squared minus 2bc cos a. Right, that's the cos rule. So we're going to use this 120, as I said, as a. So that means that L has to be little a. So substituting in, we get that. Alright, so now what we need to do is take the derivative of this expression twice. And in doing that, we're going to end up with something that has xa double dot, which is the same as the acceleration of a, and xb double dot, which is the same as the acceleration of b. and that's going to form the third simultaneous equation to be able to solve the system. So I'm going to take derivatives with respect to time. Alright, so first derivative, we know that L is constant at all times. So when we take the derivative of that, it's going to be 0. Next we need to take the derivative of xa squared, and we know xa is a function of time, so it's definitely going to have a derivative. Applying the chain rule, it's going to be the top number, comes down the front and multiplied by the 1, so it's going to be 2. Write down the variable, and it gets raised to the power of 2 minus 1, which is 1, so I'll leave that as it is. And then we multiply by the derivative of the variable itself, which is xa dot. So next one, same kind of deal, 2 comes down the front, xb, take 1 off the power, so it becomes to the power of 1, multiplied by its derivative, which is xb dot. Alright, so now we just need to deal with the last term. I'm going to bring all the constant numbers out the front, so 2 and cos 120. Remembering we said that 120, this angle, is also a constant at all times. So it's going to be 2 cos 120 out the front. And then we're going to need to apply the product rule to take the derivative of this x8, xb multiplied by each other. So for the product rule, we hold the first one as the same thing, and we take the derivative of the second part, so this is going to be xb dot. Then we hold the second part the same, so xb, take the derivative of the first part, so xa dot. So that becomes the first derivative of our equation. So one thing we can do to make it a little bit simpler is divide everything by 2. So we're going to cancel with each other, and we're left with all the rest. Alright, so we're going to need to take a second derivative so that we get the double dot in our equation. So the second derivative, again we're going to need to apply the product rule here. So we hold the first thing constant, which is xa, and take the derivative of the second part, so that's going to be xa double dot. We then hold the second part constant and take the derivative of the first part, so that's going to be xa dot as well. Now we move on to the next term. Again we require the product rule here, so hold the first part constant, take the derivative of the second part, hold the second part constant, and take the derivative of the first part. Alright, so now we just have this final bit left. So now we just need to take the derivative of this final term. So we can leave the cos 120, the constant number, out the front and just work on what's inside the bracket. So it's going to become xa xb double dot plus xb dot x dot a, xb x double dot a, xa dot xb dot. Alright, so this is the expression. You can see that we've got acceleration of a and acceleration of b inside here. So all we need to do now is kind of simplify it down and work out the numbers that need to slot into this equation for all the other variables. So I'm going to make this a bit nicer. and we end up on the end here with two of these terms. Oops. So 2xv dot xa dot. Alright. So if we want to make it a bit nicer, what we can do is replace some of these dotted terms with the velocity and the acceleration. So I might do that now just to make it a bit nicer. Oopsie, got to replace this one, maybe. Alright, so now we need to fill in this equation. So from the question we were given a couple of pieces of information. What we were told is that the velocity of A was 0.4 meters per second, and it was to the right, and that's like the positive direction, the way we assumed it above in the question. And we were also given that the acceleration of A was equal to 2 meters per second squared. So what we need is the other things to fill this in. So we need an XA, we need a XB, we're trying to find the acceleration of B, we need the velocity of B as well, and then we should be able to solve the equation. So let's start with finding the positions, XA and XB. So if we go back to our triangle, we should be able to solve for the length on this triangle. Alright, this one here. So what I'm going to do is just redraw it down here, so we have a copy of it. And what we know was that this angle in here was 60 degrees. Making this angle in here 120 degrees from before. We were told that this was 0.5 meters. And the other piece of information we know is the position of the bar. So we know this bar is at an angle of 30 degrees above the horizontal. So we can draw that in our diagram as well. Alright. So if we know two angles within our triangle, we can work out the third one because it has to add up to 180. So that makes this angle in here 30 degrees. So we can use either the cos rule or the sine rule when we have triangles which are not right angles. But for the cos rule, you need to know more than one side length. So that makes the sine rule the one that's most appropriate for this situation because we know all of the angles but only one side. So the sine rule looks like this. So the side length is the small letter and the angle is the big letter, and they need to be the opposite ones. So filling this in, if we start with 0.5 meters. The opposite angle is 120. For XA, the opposite angle is 30. And for XB, it also has an opposite angle of 30. So if you take, just for example, this part, these two parts of the equal sign, you can solve for XA. And then if you took this one and this one, you could solve for XB. And the way this triangle is, you're going to find that XA and XB are actually equal to each other. So solving, it's equal to 0.5 sine 30 divided by sine 120. And that works out to be 0.289 meters. Alright. So now what we can move on to is solving for the velocity. So that was one of the other things we needed in here, was the velocity VB. So So if we scroll up to where we took all our derivatives, what we can do is utilize the first derivative equation that we had in here. Alright. In that equation, the only unknowns were xa and xb, which we just solved for, x dot a, which is the same as the velocity of a, and we know that 0.4 meters, making the only unknown this x dot b, or the velocity of b. So I'm just going to copy down that equation. And instead of the dots, I'm going to replace each of the things with either, the velocity. Sorry, I'm just out of shot, I know, but alright, there we go. So that was our equation for the velocity, or the first derivative that we took. So if we substitute numbers in now, we should be able to solve for VB. So we just work this to be 0.289. This was 0.4. Again, we just work that out. VB is the unknown. XA we've worked out again, 0.289. VB is the unknown. So VB, only unknown in the equation, and it works out to be negative 0.4 meters per second. Alright, so now that we know all the velocities and all the positions, we should be able to jump back to our equation for acceleration up here. And we can substitute everything into it, and the only unknown is actually going to just end up being xb, alright, because we were given what the acceleration of a actually is. So jumping down here, I'm just going to substrate into the equation. So what we find is that we get something like this. Again, the only unknown is xb, and it comes out to be negative 2.37 meters per second squared. Okay, so the last step is just to go back to our free body diagrams, and we've solved our third kind of simultaneous equation to give us xb. So we should be able to just sub that in and solve for the tension in the bar, and even if we want, we can get this force in the cylinder. Alright, so let's do it off to the side over here. So let's go for this equation first. So we have negative t sine 60 is equal to the mass of b, which we know is 3 kilograms, multiplied by the acceleration of b, and we just worked that out to be negative 2.37. So tension can be solved from this equation, and it comes to be 8.21 newtons. So if we want, although the question doesn't ask, we can solve for this force in the cylinder. And it's going to be equal to the mass of A, which is 2 kilograms, multiplied by the acceleration of A, which was given in the question as 2 meters per second, plus the tension, which we just worked out to be 8.21 cos 30. so this answer comes to be 11.1 newtons. So I realize that question is a little bit of a marathon, but you kind of get there in the end. It follows the same principles as some of the other questions, which have two bodies, where you need to draw a free body diagram of each one to get two equations, and the third equation comes from looking at the geometry. So that's all I've got. See you next time.